Swayam Prabha. Digital India. Educated India.
So let me quickly remind you where we are. I am not going to be able to answer all your questions, unfortunately, within the limited time. I realize I may not be able to cover everything I wish to cover, but I don't need to cover everything I have. I will try to complete a story. There'll be gaps in the story, and I will try to answer questions to the extent I can. And I can refer you to textbooks to read. What have we learned? The universe is a large place. It is seemingly static, but it is not. It seems to be expanding with time. And the expansion is manifested as redshift of galaxies. This is what I didn't prove, but I just told you that Einstein's general theory of relativity tells us. We observe redshift of galaxies. Doppler effect seems to suggest they are moving away from us. That's not quite the correct interpretation. What you have is an expanding universe. The galaxies are located at these different grids, and it is because of the expansion of the universe, any photon left in the universe its frequency will constantly decrease with the expansion. And therefore, the wavelength will constantly increase, and therefore, the galaxies exhibit redshift, because we are observing the light as it was emitted at an earlier time when the scale factor, what is the scale factor? It is the distance between any two galaxies. And the distance between any two galaxies increases with time. When you observe a galaxy which is farther away, million light years away, you are observing when it was older. At that time, the scale factor was smaller, and therefore, its frequency was larger, right? But today, since the universe has expanded, its frequency has reduced by the time it travels, or equivalently, the wavelength has increased, which is what you observe as redshift. And that is why it's referred to as cosmological redshift. Okay? I'm going to skip all these. Something interesting happened. There was a theory which was called the steady state theory that was proposed by many people, including an Indian physicist by the name of Jayant Narlikar. It was proposed in the 1960s. That was very popular around that time. But in 1965, these people, Penzias and Wilson, came up with an interesting discovery. They were measuring the microwave spectrum from the sky. They had this horn antenna in Bell Labs in Pasadena, and they were measuring the emissions in the microwave region of the electromagnetic spectrum from different directions of our galaxy. And what they were finding was as follows. Independent of what they do with the antenna, wherever they tailed the direction, there was a buzz in the antenna. The antenna was detecting something constantly. And they could not remove this at all. In fact, what had happened was that you can see the antenna, right? It is much clearer in this here. It's a nice place for pigeons to sit down. Okay? And they were regularly dirtying the antenna. And they thought this buzz they are observing because of this dielectric material that they were leaving behind. Okay? So they kept cleaning this dielectric material, took the pigeons far away, but they could not get rid of this buzz. What they have discovered essentially is something known as the cosmic microwave background. If you want to learn an English word called serendipity, this is a ideal situation for you to understand the word. They just happened to come across this by accident. Just a few kilometers away, there was a team of physicists, other physicists, Wilkinson, Peebles, Dickey, others, were trying to construct instruments to measure this for years together. But Penzias and Wilson happened to come across this, and they didn't know what it was. Please remember this picture that you have on the right hand side here. Okay? What they have observed is something known as the cosmic microwave background. Please remember this sky. Remember this map here. Much earlier, I had talked about this Keralite Appam, right? Which is our galaxy. And I talked about something known as the 2-degree field survey, right? It measured 1 degree field north of the equator, another square degree south of the equator. So you can think of the galaxy as a plane, right? Galaxy as a plane, and you can extend it all across the celestial sky. You have the celestial sky, you have the galaxy as a plane, you can extend that galactic plane across the celestial sphere. It's called the galactic equator. So what you observe on this line is the galactic equator, and just like, you would have seen pictures of the Earth projected on an ellipse like this. It's a particular kind of projection. What has been done is that the entire sky has been projected on this ellipse, and this horizontal line here is the galaxy. So that band that you see in the middle is microwave emission from our own galaxy. There are so many stars and various objects in the galaxy, and they are going to emit in different regions of the electromagnetic spectrum. But this green patch is what they seem to be observing from virtually every direction of the sky. Now, what you would naively imagine is that you are seeing radiation from all the stars and all the galaxies in the sky, right? And they will dominate the energy density of radiation in the universe. We were trying to understand what is the composition and the evolution of the universe. I presume you understand why we are talking about evolution. The universe is changing with time. You would like to know how is it changing with time. And in order to do that, you need to know the composition of the universe. Evidently, we have matter, that's what we are made of, and there is radiation. And I would have naively thought that the radiation is in the form of largely starlight, emitted by all the stars and galaxies in different parts of the universe. What has been plotted is the intensity of the radiation as a function of wavelength due to different sources in the gamma rays, in the X-rays, in the far infrared, etc. But you can see one particular thing dominates everything else here. It's called the CMB. The energy density of radiation in the universe is dominated in the microwave region of the electromagnetic spectrum. So, and it is called a background because it seems to be present in all directions of the sky. Okay? It is microwave. I hope you understand why. Because it is peaking in the microwave region of the electromagnetic spectrum. It's a background because it is present everywhere. Okay, it's everywhere. It is not an isolated source. It's not from this galaxy or this galaxy here or this galaxy here. Independent of which direction of the sky you look at, all right, you seem to see the source. And that's why it's referred to as the microwave background radiation. It is light, it is radiation, but as we'll quickly see, it is also thermal in nature. How many of you have seen good old CRT television? Okay, you are still, okay, all right. If you are in those good old days before cable and all came up, as you turn on your CRT, there'll be a buzz in your TV. Some of those are due to these microwave photons. Okay? So the microwave photons are present everywhere, all around us as we speak. So it is, what did I say? It is in the microwave region of the electromagnetic spectrum because it peaks there. It is a background because it is not due to isolated sources in the foreground. It's present everywhere, whatever direction I observe. And it is radiation because, it's light. What this picture contains is this region, okay? The next slide contains a zoomed in portion of this region where the energy seems to peak. And it has, what has been plotted is a Planck spectrum. How many parameters describe the Planck spectrum? I'm sure all of you have heard about the Planck spectrum. No? Which class are you in? 11th and 12th standard? Going to 12th. You haven't heard of the Planck distribution? You may have heard. Okay, all right. You will hear very soon. Okay. A Planck spectrum was, it is described by one quantity called the temperature. Okay, all right. And if you give me one temperature, the curve is completely determined. So what this guy contains is the zoomed in region, as I mentioned. This is measured by this Kobe satellite. Remember, we had heard about the Kobe satellite earlier. We'll hear about it further as we proceed. And it corresponds to a particular temperature. It's called a black body spectrum. Have you heard of a black body? Okay, so the spectrum emitted by a black body maintained at a particular temperature is called the Planck spectrum. It is determined by only one quantity called the temperature. If I know one point in the spectrum, it's adequate for me to determine the complete spectrum and determine its temperature. Okay, all right. So what happens is, this is the spectrum measured by the Kobe satellite of the cosmic microwave background. What you find is that it is a perfect thermal spectrum. That is, the radiation is thermal in nature. Okay? It is characterized by one temperature, and the temperature of this black body radiation is about 2.725 Kelvin. What I want you to appreciate is that these error bars that have been indicated here have been enlarged 400 times so that they are visible in the graph. Otherwise, they will be thinner than the line drawn. Okay? So it is an exceptional Planck spectrum. You are unlikely to better it in the laboratory. So the bottom line is that, as far as the evolution of the universe is concerned, the universe contains matter, let us say as we know it, and it seems to contain radiation, but the energy of radiation is not dominated by the energy from the light from the stars, etc. The energy, most of the energy in the radiation, in fact all the energy in the radiation, the dominant energy in the radiation is in the form of a perfectly thermal spectrum, which has a temperature of 2.725 Kelvin today. There are a few other things that you need to know about it. Okay, I will not be able to explain all of this. I will try my best to convey this. If you have matter, how does its energy density change with volume? How does density of matter change with volume? It goes as 1 over the volume, right? In a universe, what is changing? It is the scale factor that is changing. So if I have a cube, after a certain time, each side of the cube is changed by the factor A. So the energy density of matter, ordinary matter, goes as 1 over A cube, roughly. Like 1 over volume. The temperature you can show of this thermal radiation goes as 1 over the scale factor. Okay? This is again, I have to turn to general relativity to explain, or at least a few other, ideas from what is known as statistical mechanics. Because it's beyond the scope of these lectures for me to explain how this arises. You have to take it for granted. That the temperature goes as 1 over A. But something you know already. How does the energy density of radiation behave as a function of temperature? There is a famous law. Someone said that. What is it called? It's called the Stefan Boltzmann's law. What does it say? That the energy density behaves as? You be careful. Energy density behaves as? T power 4. Okay? So that's the bottom line. So if the energy density, we have seen that most of the energy density in the radiation is in the form of this nearly perfect black body spectrum, And such a black body spectrum has has an energy density which is described by the Stefan Boltzmann's law. So therefore it goes as T power 4. Something else tells me, general relativity tells me, and statistical physics, that T goes as 1 over A. A is the scale factor. I presume you have digested now what is A of T. So you can immediately conclude that the energy density of radiation goes as 1 over A power 4. Now I turn to observations, right? I now turn to observation. I ask what is the energy density in what I have. Nr corresponds to ordinary matter. It's referred to as non-relativistic matter to contrast with relativistic radiation. Radiation consists of photons, so it is naturally relativistic. One finds that the energy density in radiation is about 10 power 4 times smaller than the energy density in matter today. Yeah? Had it been otherwise, we would have been fried. We wouldn't have existed. Right? Now, given that energy density of non-relativistic matter goes as 1 over A cubed, and the energy density of radiation goes as 1 over A power 4, what do you expect to happen at early times? So let me plot two curves. I can pull this down. There was a chalk somewhere here. So I'm going to plot logarithm of A. And I'm going to plot logarithm of rho r and logarithm of rho nr. How will, given that rho r goes as 1 over A power 4 and rho nr goes as 1 over A cubed, how will these functions behave in this plot? Can someone make a guess? So log rho r is what? Log is proportional to A power 4 plus constant. Right? So what is this? So it is 4 log A plus constant. And similarly, log rho nr is 3 log A plus constant. So what will be the nature of the curves? There will be straight lines with different slopes. Okay? So let me draw them. One which will have a sharp slope, right? And one which will have a, correct? Which one is radiation? The one which falls sharper is radiation, and one which falls, so this has a slope of 4, this has a slope of 3. Okay? So for instance, if I plot this, is there a duster? Yes. Sorry? Oh yeah, it's yes, -4. That's why I've drawn it like this. Yes, that's right. Yes. Okay, correct. Thank you. So you can compare, for instance, energy density of Nr. Let us say this is today. Right? This is logarithm of A. Right? Let me erase this. Okay. So what you find is that this is rho r. Okay, this is rho nr. This is 10 power 4 times smaller than this today. Right? We can estimate the energy density in radiation easily because it is given by the Stefan Boltzmann's law and we know its temperature. Okay? But what can happen? This is the time when the energy density in radiation and matter are equal. Right? They are crossing. But at an earlier time, what happens? No, this is the time. So what dominates here? What dominates here? So I will call this as matter domination, right? Today matter dominates. If radiation was dominated, we would have been, we would have evaporated possibly. Okay? But at early time, before this time, what happens? Radiation dominates. Okay? So the fact that there is matter and there is radiation which is thermal in nature is adequate to tell us that at very early in the universe, it was dominated by radiation, and that leads to this picture that we have, namely the hot Big Bang model. Universe is expanding. As I run this movie backward, it seems to end in a bang, right? It seems to start with a bang. It seems like all the galaxies were on top of each other. You can imagine there was a big bang which caused this explosion, making these movies fly away from each other. The fact that there is, radiation and matter present, and we know the temperature of the radiation today, and we know this ratio, which tells us that very early in the universe, the radiation was dominant. It was much more dominant than compared to matter. And it clearly tells you that, as the very first line of this title song of the Big Bang Theory, I presume you know someone like Sheldon, okay? So it says, our universe was in a hot, dense state. So there was a Big Bang. The universe started in a hot, dense state, okay? That is why it's called the hot Big Bang model. It started with a hot, dense state. What happens? It is expanded. We know the energy density of radiation falls as 1 over a power 4 like this. The energy density of matter goes as 1 over a cubed. As a result, there comes a time when the universe cools and stops being radiation dominated and transit to matter domination. So this epoch is called radiation domination for obvious reason, and this epoch is called matter domination. And then what is the CMB? It is not difficult to understand. It is just the radiation from this epoch. This yellow fluid here corresponds to very early, this corresponds to very early times, and this corresponds to very late times. And this transition that seems to be happening occurs around an epoch somewhere here. Okay? I will not be able to go into the details, but you will be able to understand what is the origin of the CMB without difficulty. This yellow fluid here is radiation, right? These large red balls are supposed to be protons. The small green balls, can you make a guess? Electrons. The large green balls? Neutrons. So this is, what is this? These protons are nuclei of hydrogen atom, and these are nuclei of helium atom. What happens? What is the energy that is required for a photon to remove an electron from the hydrogen atom? So you know that. So what essentially happens is that when there is high temperatures, the photons have higher energy. So one of these green balls, small green balls, is trying to either combine with this proton, either the nuclei of the hydrogen or the helium atom. But a photon quickly comes in, which has high enough energy, knocks it off. Therefore, very early in the universe, right, it is difficult to form atoms of hydrogen and helium. But what happens? As the universe expands, the energy density in the radiation comes down. How does the energy density go as temperature? It goes as T power 4. If the energy density is coming down, which means T is coming down, if the temperature is coming down, Kb, you know what is Kb? The Boltzmann constant time T, which is the average energy in the photon, is also coming down, which means after a certain time, there comes an epoch when the photon is not able to ionize or the helium atoms. And what happens? The photons are not able to do anything. They start streaming freely. And what are these clouds here? The atoms, the electrons have combined with the helium and the hydrogen nuclei to form the hydrogen and the helium atoms. And this CMB, these photons that you see here, which are traveling freely, from that time until today, they are hardly affected by anything, and they start traveling towards us, and which is what we observe as the CMB. And this is a nice way of thinking about it. I'll finish this slide and come to you. So think of a cloud, right? There are photons inside the cloud. Isn't it very stuffy here? Can we have the AC? Can we have the AC, please? Okay. Sorry. Okay. Okay, he's hesitant. Be brave. All right, thank you. All right. So what happens is as follows. You have the photons which are here, and there is a cloud. What does the cloud consist of largely? Water molecules. So you can think of a photon which is trying to escape the cloud, but it's not able to escape. Why? Because it is colliding with the water molecules. Okay? But suddenly it comes to the edge of this cloud, right? Then what happens? Suddenly this photon is free to travel and hit your eye. And what do you observe? You observe a cloud. You observe a cloud. That is what is happening here. So if you look at different directions, if you keep looking at different directions, you're looking at the universe as it was older and older. So you'll end up the Big Bang singularity. But not only in this direction, any direction I look at. Right? Okay? And that's what this Big Bang singularity is. It's a sphere around us. Because as you look at a direction, you're looking at as the universe was older. I have to look at as old as the universe is to hit the Big Bang. Is that clear? And here is what I refer to as the surface of last scattering. This is this time. This is plotted as a function of time, I hope. There comes this epoch when the photon is not able to ionize the hydrogen atom. And notice, and that corresponds to a particular point in the sky. And not only one given direction of the sky, in all directions of the sky. Do you appreciate that? Is this clear? And that's called the last scattering surface or surface of last scattering. That is the last time the photon scattered off an electron. Thereafter, the photon is traveling to us freely from all directions of the sky. All directions of the sky. And which is what we observe as the cosmic microwave background. Okay? So, so you have a sphere, which is the last scattering surface. You have seen this, you have seen this picture of the earth with different temperatures illustrated. In the same manner, I can take the sphere, project it onto the ellipse, and show the temperatures in different regions of the sky. Is that clear? Okay, you've been waiting for long.
So, at one point, the radiation and matter doesn't ever.
That is correct.
So why take it? Why not?
Oh, because there are two scales. It's a very sophisticated question. Okay, there are two scales in the problem. It is like this. I'm trying to see. Imagine there are people in this room. Okay, if you are moving very slowly, and there are a certain number of people in the room, there is a density of people in the room. If I'm moving very slowly, okay, I will not interact much. But if I'm rapid, there is a possibility of interaction. So there is a rate of interaction between electrons and photons. Okay, that is one time in the problem. But there is something else that is happening in this universe. In this room, imagine this room is expanding. That will also change the rate at which I'm interacting. Yeah. So when they are comparable, they become they can stop interacting. Yeah. It's called decoupling. Yeah. Any other question? Very quickly.
Sir, why do we have peaks and valleys in this matter?
Very good question. I'll come to that. Okay. So I have, how much time? Can someone tell me how much more time can I take? When should I complete? I have to finish in 5 minutes. Okay. So I have to narrate the story. I have to finish narrating the story in about 5 minutes. Okay. So I'm going to skip a lot of this. I'm going to skip all of this. All right. So there was this question. This is a larger picture of what we had earlier. Okay. Someone was asking, what are these different colors correspond to? This is essentially the CMB sky. Okay. What I mean is that I measured temperature in different regions of the sky, and that has been illustrated. Evidently, it was not completely green like Penzias and Wilson observed. Okay. What we find is that the temperature of the CMB sky is virtually the same up till the 3rd decimal place or 4th decimal place. That is, it is 2.728. Is the same in all directions, but if I start measuring that at the 5th decimal place, the temperature of the CMB sky is different from one region to another. In other words, there are anisotropies. The anisotropies, as you can imagine, if it is differing at the 5th decimal place, if I measure the deviation in a particular region when compared to the average temperature, delta T by T should be 10 power minus 5. Okay. So at this time, when the universe decoupled, right, at the last scattering surface, I hope you recognize that this is essentially a picture of the last scattering surface. Okay. The picture of the last scattering surface, and at that time, there was very tiny fluctuations. Okay. Since I have limited time, what I am going to show is how these tiny fluctuations grew into the large-scale structure today. I'm missing out a lot of points. I want to explain an idea called inflation, etc. But there are 2 parts to the story. One is what caused these perturbations, right? Tiny fluctuations, because we have assumed that the universe is homogeneous and isotropic. There should be something that causes these tiny fluctuations. And somehow these fluctuations should grow into the structures that we see around us today. Okay? So I'm just going to play movies, for want of time to highlight these points. So let me stop this. So what happens is as follows. Very early in the universe, it's like still water. There were no fluctuations, right? The universe was indeed homogeneous and isotropic. But the universe at very high temperatures is not described by classical physics. It's described by something known as, make a guess, quantum physics. And what happens in quantum physics, in contrast to classical physics, is there are fluctuations. And these are inevitable. They are unavoidable. And there were fluctuations. And what happens is, there are tiny fluctuations that were generated in the early universe. Okay? Because fields that are present at very high energies, it is very much like throwing stones in a pond. And these fluctuations are what gave rise to these anisotropies in the CMB that you said, that I illustrated, I showed in the previous slide. Then what happens? So remember, the anisotropies in the CMB comes to us from, where is my chalk? Okay, comes to us from such an epoch, from this epoch, around this time here. Okay, I'm not indicating any numbers, I'll be glad to explain them later. Now, during this epoch, it is dominated by matter. When you have, so what is happening? Initially, we thought it was smooth, but I just showed to you that there are fluctuations in the early universe that induced small deviations from smoothness. We already know, if I look at, I said delta T by T is like 10 power minus 5. What is this? This is the anisotropies in the CMB that I observed. Okay? If rho r is some sigma t power 4. What is delta rho r by rho r? Or capital delta rho r? How is it related to delta t? What is delta rho r? It is just sigma 4 t delta t divided by sigma t, t cube delta t. So this is sigma, sigma goes away. So it is 4 delta t by t. If delta t by t is 10 power minus 5, delta rho by rho is 10 power minus 5. So this assumption that the universe was initially homogeneous and isotropic, which was very smooth, is a correct assumption. It is confirmed by the observations of the anisotropies in the cosmic microwave background. Then what happens? I will again show you a picture, show you a movie to illustrate this point. So let me just stop that movie. So what do you have? You have anisotropies in the CMB. And you have crossed this epoch. You have crossed this into the matter-dominated epoch. So what is happening is that delta rho by rho induces delta rho by rho in matter. There is radiation present, there is matter present. During the radiation-dominated epoch, nothing can collapse because of pressure of radiation. This is you may learn about it later. But here there is no radiation present. So there is matter. And there is there are what is referred, there are delta rho by rho. It is no more smooth. What will happen if there is no more smooth? If they are not smooth? It will collapse to form structures, and that is what you have here. Okay? So you have clouds of gas. What this represents is a cloud of gas, helium and hydrogen gas essentially. Okay? What is happening? They are not uniformly distributed. And as a result, they collapse. They collapse, and what will they do? They will form stars. And these are the first stars in the universe. This is the first time in the universe that there was light other than in the CMB. And therefore, it is referred to as, can you give it a name? Sorry?
Let there be light, I don't know.
No, but I want a name, right? That's not, I didn't ask for a slogan. When do you see light? It's called cosmic dawn. Okay? So this is the first time when you saw light in the universe other than the CMB. Now they form many, many stars, and you can see there is a pattern that is emerging, which is, this is a numerical simulation, and you can see very similar to what you observed in the sky. Okay? So I'll just play one more, and I will quickly wind up in the next few minutes. So here is a rough history of the universe. Okay? I'll take 2 to 3 minutes and wind up. There are many parts of the story I didn't explain. There was a big bang. Actually, there was an epoch called inflation, which I promised to spend time on. I could not. And they generated quantum fluctuations, and they gave rise to the CMB. And look at this period between the CMB and the first stars. These first star is cosmic dawn. Between these two periods, there was no light in the universe other than the CMB. And they are referred to as dark ages. Okay? And then the stars begin to form. There are galaxies which are formed. And there are some other observations. Again, for want of time, I couldn't explain. There are reasons to believe we are going through accelerated expansion. In the next set of slides, what I'm going to show is a different version of the movie I had shown as to how tiny perturbations at this very early times, I talked about what a perturbation is, can lead to the formation of galaxies in the universe. Okay, I'm just going to skip this. Right. There it is. I will let it play and then I will play it again. Notice what happens to redshift. The redshift is decreasing, which means it is coming closer and closer. It's later and later in time. Let me play this again. What you will see is an almost smooth distribution of matter in the universe, but there are tiny deviations from smoothness. Okay? I will not be able to hold it, but you can see that. There it is. What happens? The moment I have tiny deviations from smoothness, what introduces these deviations from smoothness? Quantum fluctuations. Okay? And the moment I have that, I end up with a structure, a collection of objects, which very much like the distribution of galaxies in the universe. And all this story, okay, I'll skip this part, lead to the standard model of cosmology. I haven't explained all these aspects, but I have summarized here. The universe is homogeneous and isotropic at length scales of the order of 100 megaparsec or so. I've been able to explain this. Baryons, I couldn't explain this. What you and me are made of constitute less than 5% of matter in the universe. About 25% is cold dark matter, and 70% is something called dark energy. Again, you have to ask them to invite me again to give a talk, then I can explain the remaining parts. Okay? Again, I didn't touch about how an early epoch known as inflation give rise to quantum fluctuations. All right? But I tried to use the movie to explain how these inhomogeneities leaves their imprints as anisotropies in the CMB. And using the movie again, I have explained how just conventional Newtonian gravitational instability, once you have these tiny inhomogeneities, it can lead to the structures, the cosmic structure, namely clusters and clusters of galaxies that we observe around in our universe. And there are various ongoing missions which continue to observe our universe, and there is a large amount of data that is expected to pour in, which helps us understand. In fact, apart from the electromagnetic spectrum, there is a completely new window to the universe that have opened up. Do you know what that is? $100 for whoever gives me the word. There it is. Okay, remind me. Okay? So gravitational waves. There is a completely new window to our universe that has opened up, which provides us complementary view of our universe, and that helps us understand the physics of the early universe very well. Okay? And, I'll just leave you with these two books. You should read Weinberg's First 3 Minutes. It's somewhat old. It's still a very good book. And, there is a book by Barbara Ryden, which you may want to start reading. It's an undergraduate text. Some of the others can be advanced. This book, you may begin to understand the early chapters, and the later chapters may get technical, but it persists, it'll pay off, and you will learn some aspects of cosmology. Thank you for your attention. I'll stop here. I'll be glad to answer as many questions as time permits. Yes?
As time progresses, the order at which we need to measure in order to observe homogeneities and also.
Say that again.
So as time goes, the size of our measurement in order to observe homogeneity in the universe, will that also increase?
No, that is correct. The range of the universe that we can observe becomes larger. But the problem is that what I did not adequately emphasize is the time scale of the universe. I told you there is only one place where I urged you to calculate the time scale of the universe, which is the slope of this graph, where we had V versus redshift, and there is something called H naught, which is usually quoted as 72 kilometer per second per megaparsec. Okay? This H naught inverse roughly sets the age of a universe. But that's very large, okay? But nevertheless, we have close to 100 years of observations of galaxies, and there are efforts to measure whether things are changing. What we would have referred to as constants are changing with time. Any other question? Yes. Okay, so what, I'm just going to use the slides, okay? Okay, so in 2 minutes, all right? So what I have plotted is the distance. It has been plotted slightly different. Earlier, this Hubble's law, right? I had plotted velocity as a function. I shouldn't say red. This is wrong. This was plotted as a function of distance, okay? In a modern parlance, because we don't attribute a velocity, it's not because of the Doppler effect. What is plotted is something called a distance to the galaxy. To be specific, it's called a luminosity distance. It's plotted as a function of redshift. The Hubble's law corresponds to this linear relation. At small redshift, it is linear. Okay, you can see it's a straight line. But what happens is that at large redshift, there is a deviation from linearity. And the manner in which it deviates from linearity tells us the constituent of matter in the universe. And what you find is that, there are, I haven't introduced these parameters. This guy in blue tells us the universe is completely matter and it doesn't have this constant, cosmological constant. Okay? And this red guy tells you it is all cosmological constant, there is no matter. This guy tells you, this green tells you there is 30% matter and 70% cosmological constant. Amongst the three curves, it is clear, three possibilities, it is clear that the green one fits the data very well. So what you seem to require in order to explain this data, I told you, you have rho NR and rho radiation. I told you only these two. In addition to this, there is something else that is present, which is like this. Okay, I hope I got the scale right. What is this? This is what is referred to as rho lambda. It's called a cosmological constant. It's an energy density which is bizarre. You would have thought if the universe expands, its energy density will be diluted. But the energy density of the cosmological constant does not change with time. It's not diluted. It remains the same. And in fact, today, remember this is today, the energy density of non-relativistic matter is much more than energy density of radiation. But in fact, the energy density of the cosmological constant dominates even that of non-relativistic matter. And this quantity, which does not change with time and remains a constant, is called the cosmological constant. And it's sometimes referred to as arising due to something known as a quantum vacuum. Quantum vacuum. Oh, no. No, let's not stretch those things. Okay? What essentially means is that you would have naively thought vacuum classically implies no energy, but not so in the quantum. Even though you think there is nothing there, there can be energy present. And some people think it is due to some quantum vacuum. It is? No. Okay. So it is, the only thing we are able to say is its energy density does not change with time. What is its origin? It's not clear. There are various claims that are made, but those are not confirmed. Maybe one more question? Yes.
So, what is the proof for the dark matter, dark energy?
So, this is the slide. Okay. So, I'm just going to quickly go through this. So, what you expect is as follows. This is the M33 galaxy. I had talked about it earlier, right? And using Newtonian dynamics, you can ask what should be the velocity given a certain matter inside, right? Centrifugal force, okay? You can count, and gravity, you just have to equate them. And you will obtain, if the matter is only visible, the galactic rotation curve should have come down. How do you observe the galaxy rotation curves? You can observe, they are not visible, but in what is known as 21 centimeter radio, it's not visible to the naked eye, our eye. In 21 centimeter radio observations, you can measure the motion of these objects. They are rotating with the galaxy. Okay, they are not in visible region. Okay, so what is happening is that you need to include additional matter in order to explain. This is the data. This is what should have been from the visible disk and Newtonian physics. Okay, if you need to explain this data, you have to assume that I told you about a flat galaxy, that there is a spherical distribution of cold dark matter in the universe. Okay. Another example is something you asked about, is gravitational lensing. Okay. This is essentially what you have is that a faraway source, and there is a large galaxy which contains a halo of dark matter. Okay. And I see the lensing of the background galaxy. By the extent to which it is lensed, I can determine the mass of the intermediate galaxy. Is that clear? There is a farther away source, there is a galaxy in between, and I am observing here. And this intermediate galaxy is acting like a lens of the faraway galaxy. Okay? That allows me to determine the mass of this galaxy, because all mass participate in the gravitational lensing, whether they are visible or invisible. And by the extent of lensing, I can say that this galaxy, intermediate galaxy, contains dark matter. There are various amounts of, various observations that point to the presence of dark matter. Sorry? Because there is visible mass, okay, but the lensing indicates the mass should be higher. Is that clear? I can't see the mass. And there is something called micro lensing, etc. There are various, I don't see anything there, but I see lensing. Okay? Imagine there is a source which is going like this, light source, and there is something present here. It will lens. And in fact, when it is, oriented exactly, its brightness will go very high. This is known as micro lensing. Okay? And using that object, you can see that there has to be an object in between. Now, what that object is, you don't know. It's certainly not a star, otherwise you would have seen it. Okay? There can be variety of dark matter. There could be a collection of particles. There could be planet-sized objects. There is something called primordial black holes. There could be, many types of dark matter that are being present. But it is clear that dark matter is present. What is the nature of dark matter? What is the constituents? What are the different possibilities? How much of different things contribute to dark matter? All these are not clear at this stage. Okay.
Sir, is there any other theory other than dark matter which can explain these observations that people have made?
There was a theory that was popular, but I think I'm not an expert in this, something called modified Newtonian dynamics, which was able to explain the rotation curves of galaxies. You modify the Newtonian law, but I think it is increasingly not favored by the data. So as of now, dark matter is the best way to explain what is known as rotation curves of galaxies.